Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Karmila, Mititadil Hari Osman, metric number A25 CS0330. And in this project, I am in charge of stress testing the Intel Core i5-10300 this laptop to identify its microarchitectural boundaries by using the benchmarking tool Passmark Performancetest version 11.1. So we are moving beyond high-level software scores to investigate raw ISA throughput and ISMD efficiency.
Passmark Performancetest application. So to maintain rigorous testing standards, this laptop was connected to an AC power in best performance mode to eliminate power saving throttling. Okay, so in order to run the test, firstly for workload A, we go to CPU mark, and then here, this is the meter, CPU mark meter, and then there's the test that we can run. So for workload A, we're going to run integer math, which is going to take only a few seconds. It's not going to be that long. Alright, and here shows, and then here it'll show the result, the number and the percentile, the comparison to the rest of the world. Alright, and then we're going to run floating math. Floating point math, sorry. Here is the result, and then run sorting. Alright, and here is all the results that we have obtained. So here you can see the numbers. So in order to save the numbers, you can go to File, and there's save results as image, text, or web. You can choose whatever results that you want in, and for this one I'm going to take save results as text, and then just save it. Alright, and then it'll show on your folder. Okay, so next for workload B, we are going to run tests for run test. Run test for floating point math and extended instructions SSE. So here, just the same like our workload A, we're just going to run and wait, and this is going to be the result, and then here's the number showing the million operation per second, and then the extended instructions. Here it will show the number, and then you can also save this one, save the results, and then it will save in your folder.
So to ensure that the data that I've captured is statistically significant, every test for workload every test for workload A and workload B was repeated across multiple iterations. 4 iteration for workload A and 5 for workload B to neutralize background OS level scheduling noise. So let's look here at the data. So here I have performed 4 distinct iterations. The average integer math score here of 29,041.9 million operations per second proves high ALU utilization. However, look here at the sorting score, which is 16 16,526.1 thousand strings per second. This is proportionately low. This is proportionately lower than our integer throughput. From a COA perspective, this confirms an L3 catch fill bottleneck. Because sorting is branch intensive, the pipeline experiences frequent stalls, proving that our architecture is limited more by memory latency than by raw arithmetic processing power. So, next, moving on to workload B. Moving on to workload B. Here is the data. I have performed 5 different iterations for the SIMD slash vector suite. So to guarantee position, I have run 5 iterations. So I have recorded an average SSE throughput of 8,307.9 million matrices per second. The performance delta here compared to workload A highlights the architectural cost of vectorization. So it's clear that while the i5 architecture for this laptop excels at standard scalar math, the vector path throughput is bound by data path bandwidth to the cache rather than the raw FPU clock speed. So, the benefit and limitation for this benchmarking, we've achieved high granularity ISA profiling. So here we're just reading a score. We are mapping execution latency. However, we face two critical limitations. OS-induced scheduling jitter, where Windows kernel interrupts introduce minor variance across the iterations, where Windows and thermal temporal decoupling. Because Passmark doesn't log real-time junction temperatures, we are observing peak capacity performance because we cannot definitively handle separate architectural stalls from thermal induced frequency scaling without additional telemetry. In summary, uh, the system is optimized for general purpose, integer heavy tasks. Our analysis confirms that for complex parallel rendering, the system is constrained by memory latency rather than raw clock frequency. For future work, we recommend hardware-level telemetry correlation using HWin FO64 to link these SIMD boundaries with thermal and power limits. So, this project has provided us, me and my other team members, with a direct look into the hardware-software interface. That's all from me. Thank you very much.